Hey everyone, we're about to jump into a math puzzle that honestly, it seems like it should break the rules of logic. It's one of those things that just feels impossible. It's called an infinite geometric series, and I promise you, understanding this is like learning a secret password to some really powerful ideas, not just in math, but in finance too. So, let this sink in for a second. Can you add numbers together forever and still get a finite answer? I mean, think about it. If you just keep adding positive numbers forever, the sum has to just get bigger and bigger, right? It should just spiral out to infinity. I mean, that's just common sense. But what if I told you that sometimes, just sometimes, infinity adds up to a simple, single number? Okay, let's make this real with an actual example. We start with the number 1. Simple enough. Then we add half of that. Then we add half of that, which is a quarter. Then an eighth, and we just keep doing this forever. Now, yeah, each piece we're adding gets smaller and smaller, but we're still adding an infinite number of them. So what do you think the final sum is? Is it just infinity, or is it something else? So to crack this puzzle, we need to understand this one all-important rule that basically governs the whole thing. It's this one simple condition that acts kind of like a switch, you know? It decides if our infinite sum is going to land on a nice, neat number, or if it's just going to explode into infinity. And this condition, it's called convergence. All it really means is that a series converges when the total sum, as you keep adding terms, gets closer and closer to one single finite number. Think of it like this. Imagine you're walking towards a wall. With your first step, you cover half the distance. With your next step, you cover half of what's left. You'll keep getting closer and closer. In fact, you'll get infinitely close, but you'll never actually pass the wall. That wall you're approaching, that's the sum.
And what decides between these two fates? Well, it's surprisingly simple. It all comes down to one little value we call r, or the common ratio. That's just the number you're multiplying by each time to get the next term in the series. And here's the rule. If the absolute value of that ratio, so basically its size without caring about the negative sign, is less than 1, the series converges. It's all good. But if it's 1 or bigger, the series diverges. The sum just blows up to infinity. That's it. That's the whole test. Okay, so let's say our series does converge. How do we find that exact number it's heading for? Well, this is where we get to unveil the tool that makes it all possible. It's a really, really simple formula that basically tames infinity and turns it into something we can solve with basic arithmetic. And this formula, it's not just magic, it's pure logic. It actually starts with a formula for a finite series. Now just think about what happens as n, the number of terms we're adding, starts heading towards infinity. Remember, our r has to be a fraction less than 1. So what happens when you multiply a fraction by itself over and over and over again? Well, it gets smaller, right? Incredibly small. That r to the power of n part of the formula just shrinks and shrinks until it's basically 0, and it just vanishes from the equation. And look what we're left with. The final sum, s, is just the very first term, a1, divided by 1 minus the common ratio r. That's it. That's the whole secret. An infinite number of things to add up, all solved with one clean, super powerful equation. Okay, enough theory. Theory time is over. Let's actually put this formula to the test and finally solve that puzzle we started with. All right, here we go. Back to our original series. The first step, as always, is to figure out our two key variables. So our first term, a1, that's easy. It's just the number we start with, which is 1. And the common ratio, r, well, what are we multiplying by each time to get the next term? We're always multiplying by 1/2. Simple. But wait, before we jump ahead and plug anything into that formula, we have to do the convergence check. This is absolutely critical. Is the absolute value of r less than 1? Well, the absolute value of 1/2 is just 0.5, which is for sure less than 1. So yes, it converges. We are clear to go ahead and solve this thing. Okay, now for the fun part. We just plug our numbers into the formula. The sum is our first term, which is 1, divided by 1 minus our common ratio, which is 1/2. So that's just 1 divided by 1/2. And the answer to our big infinite puzzle is exactly 2. Wow, all of those infinite little pieces add up perfectly to the number 2. All right, that is pretty cool. But here's where this whole concept gets really clever. What about a repeating decimal, like 0.333 and so on? I mean, that doesn't really look like a series at all, does it? But it turns out it's a perfect infinite geometric series, just in disguise. Let's break it down. We can rewrite 0.333 repeating as 3/10 plus 3/100 plus 3/1000, and on forever. And just like that, boom, we have a series. Our first term is 3 over 10, and to get from one term to the next, we're just multiplying by 1 over 10 every single time. So, first things first, we check, is the absolute value of 1/10 less than 1? Yep, it sure is. So we can use our formula. We take the first term, 3/10, and divide it by 1 minus 1/10. Do the math, and what do you get? Exactly 1/3. This is the actual mathematical proof for something you've probably just taken for granted since grade school, that 0.3 repeating is 1/3. How cool is that? Now, this formula is super powerful, but honestly, it's also really easy to make a simple mistake with it. So let's go over the most common traps so you can make sure you don't fall into them. Trap number 1, and this is the big one. Don't ever use the formula if the series diverges. You just can't. You have to check that R value first. Number 2, be super careful with negative signs when you're calculating the bottom part of the fraction, the denominator. That's a super common mistake. And finally, always remember the rule is about the absolute value of R. So a ratio like negative 0.8, that still converges because its absolute value is just 0.8, and that's less than 1. Let's just zoom in on that sign error for a second. Let's say your R value is negative 2/3. It is so easy to mess this up in the denominator. But you have to remember, the formula is 1 minus R. So it's 1 minus times negative 2/3. And those two negatives, they cancel out and become a positive. It's a tiny little detail, but I'm telling you, it's often the difference between getting the right answer and the wrong one. So right now, you might be thinking, okay, this is a neat little math trick. But what if I told you that this exact same logic is used to make billion-dollar decisions in the world of finance? Yeah. Let's see how this abstract math translates directly into real-world money. You see, in finance, there's something called a perpetuity. It's an investment that promises to pay you a fixed amount of money, let's say every year, forever. An infinite stream of payments. Does that sound familiar? So here's the multi-billion-dollar question. How much would you pay today for the right to receive $100 every single year for the rest of time? Your first instinct might be, well, an infinite amount of money. But it's not. Using a 5% interest rate, or what they call a discount rate, the answer is exactly $2,000. Now, the standard formula they teach you in finance is that the present value is just the annual payment divided by the interest rate. But wait, look closer. This is our infinite series formula in a brilliant disguise. The first payment of $100, that's our A1. And the common ratio? That actually comes from the interest rate. See, because of interest, money in the future is worth less than money today. So each future payment gets discounted, making it a smaller and smaller piece of the total. That discount factor, that's our R, and it's always less than 1. It is the exact same logic, just with different names. So think about that. We've gone from a simple little number puzzle all the way to the foundations of modern finance, and it's all powered by this one elegant idea. What the infinite geometric series really teaches us is that some things that seem impossibly huge and endless can actually be wrapped up and understood with some pretty simple logic. Which kind of leaves us with a fascinating question, right? What other infinite patterns are out there in our world that might just have a simple, finite solution waiting for us to find it?